Welcome to another session of Meet the Scientist. I'm Bonnie Murray, and we'll get into a little more of introductions in just a second. But first, let me explain Meet the Scientist sessions. These are a part of the Arctic and Earth Signs project, and I am going to share a slide, I hope, and tell you a little more about that. There we go. Let me just switch over here and do that. Okay, so you're seeing the Arctic and Earth Signs logo, and you're also seeing the link underneath to be able to go to that link to learn more about the project. Arctic and Earth Signs is a NASA-funded project run out of the University of Alaska Fairbanks. It involves training in global learning and observations to benefit the environment. And more importantly, it involves grading the globe data measurement and the globe work in with indigenous knowledges and community input into what is being researched. So communities all over Alaska and the lower 48 are participating. They are coming up with research questions to investigate something that is of interest in their community. And then they're adding on and braiding in the globe piece to be able to do monitoring and collect data about whatever that topic is that they are studying. So we are connected today. Let me stop sharing this. We are connected today, with Deshana York. So you're seeing Deshana up there, and I will come back to you in just a second. But I'm referring to her now to mention that that's the community in Anchorage, Alaska that has been participating in this workshop and doing some globe data collection and monitoring. We have with us today Ralph Lorenz. And you'll see Ralph there in one of the Hollywood Squares boxes. And Ralph is a researcher and he is working on the InSight project. So InSight is a satellite, not a satellite, sorry. I always want to say rover, Ralph, don't I?
It's a lander.
Yeah. InSight is a spacecraft that is now on Mars, and he'll be telling you more about that. And it is collecting data. So as we talk about that globe data piece, collecting data, that's what InSight is doing. And it is a solar powered instrument. And so Ralph will be talking to us about the solar power that's involved with that as well. So regarding introductions, let's see. Ralph will be hearing from you in a minute. I want to say hello to Elena Sparrow. Elena is the PI on the Arctic and Earth Signs project. Elena, would you like to say something?
Oh, I'm so glad to be here and participating, and welcome to everyone. Thank you for taking time out to join. And of course, I'm grateful to Ralph for making time to be the one explaining to us and being our scientist. So thank you. Thank you, Bonnie.
Pleasure.
Most welcome. Thank you, Elena, for all the work that you do making the project possible, doing all the work to pull the actions together. Christy, would you like to say hi? Christy Buffington is also part of Arctic and Earth Signs.
Well, hi, everybody. I have my son painting behind me today because I'm super excited to learn about the solar-powered NASA science on Mars. Thanks for coming today. And this recording, I know, will be used by some people in their classrooms. So teachers have reached out to me saying they wanted the recording. They couldn't join, but they're going to use it with their students. So thanks so much, Ralph, for doing this.
Right.
Awesome. And Christy and Elena are both connecting from Fairbanks, Alaska.
We have Candy Deerenfield here too with our project.
Okay, go ahead and say hi, Candy. I think you're still muted. It's sometimes.
Sorry, I had to find the unmute button.
Yeah.
Hi. I'm the Alaska State 4-H program leader, and I also work with Elena and Christy and Deshana on the science project, Arctic Earth Science Project.
Okay, awesome. Well, we're very glad you're here with us today. Great. All right. So thanks to NASA Science Mission Directorate for funding this work, the Arctic and Earth Science Project, and for the funding that makes all of this part of the Meet the Scientist possible. And thanks for being here, Ralph. And we will go turn it over now to Deshana to tell us a little more about the project that's been happening and a little bit about what it's like in Anchorage at this time. And I think you're still muted, Deshana.
Sorry about that. I hit the button and nothing happened. I said hi, Bonnie, and hi to everyone that's on today. And I did want to also recognize Candy as being our program leader. So thank you for introducing her. As you mentioned, Arctic and Earth Science has been integral into the process for today's session. But also I wanted to let everyone know that Alaska 4-H is a big partner with Arctic and Earth Science. And so Candy, as was introduced, is, kind of our linkage to Alaska 4-H and the Arctic and Earth Science Project. And so it's been a pleasure to work with her and with the team at Arctic and Earth Science to be able to bring a lot of STEM and informal education to our 4-H members and at large youth around the state of Alaska. So right now, you asked about Alaska. It's winter, of course, and so the time of year it played into a little bit of this project, which you'll hear about from some of our participants. But Alaska 4-H, being a partner of Arctic and Earth Science, did a special STEM project, which is what we're following up with you and with Dr. Lorenz about today. So in celebration of Energy Awareness Month in October and also the 4-H enrollment year, Alaska 4-H partnered with REAP, the Renewable Energy Alaska Project, to put together a solar-powered rover STEM challenge. So National 4-H was doing a kind of a mission to Mars theme, and so we tied in with that and decided to partner with our lovely folks at REAP to do some STEM education around solar energy and utilizing the kits from a National 4-H to put together this solar-powered rover STEM challenge. So the planning team consisted of myself, my colleague Ann Biddle, who works in 4-H as well at Cooperative Extension Service here in Alaska, and two of our friends from REAP, again, that's Renewable Energy Alaska Project, Colleen Fisk, who is the Energy Education Director, and Tyler Katzmar, who's the STEM educator. I know Tyler's on with us today. I didn't get a chance to see if Colleen was on quite yet, but they were instrumental in assisting us with this project, and it was great. So participants signed up to join 4-H, and when they did, in recognition of the new 4-H year that started in October, they received a kit from us that consisted of materials to help them build their rover. So REAP also participated and provided solar panels to be placed on the solar rovers as it was for them to create and then to have a challenge for a design project. So we had 3 fun interactive virtual meetings along with the design. We had a technical session to talk with them about their build design. They asked questions and they brainstormed about their project, and Tyler led that discussion. It was awesome. And he, gave them a lot of tips and tricks on some of the mechanics associated with solar installation for their rover. And then we had some interactive discussions with Alaska solar researchers who were actually doing solar research in the state here. And also we had a solar installer join us for another session. So we got to talk and ask questions of an actual solar installer and what that was all about. So participants submitted their challenge projects via video. They sent us a 3 to 5 minute video, and our team judged those projects, and we had 3 top winners. And I'm going to show you a quick video right now of our top two winners from our challenge who are actually on with us today. So here we go.
Calder, Prussian, and I'm 13, and I'm in Sitka, Alaska. My design process was I wanted to get the most amount of solar power to my solar panel as possible. So I had a few design ideas, like I had a pencil here so the solar panel could rotate back and forth, but that didn't really work. So I just have the solar panel on the top here to get the most amount of solar energy. And then the cardboard is also cut so it fits into the bottom piece here. And so it's really stable, so the solar panel doesn't move around and the electronics on the inside don't get damaged. And then also on the tires, there's like a rubber strip around both of them, so it can get more traction to if you want to go places or go faster, and so it doesn't skid out too. And I learned that in Southeast Alaska, getting solar energy is really challenging. So I had to add batteries in there, and I learned also that you have to design the frame like around the gears and the motor, and it would go across the floor and kind of like move around a bunch and spin around. And so once I put the rubber, the rubber on the tires, it went more straight and more efficient instead of skidding a bunch. For my rover to Mars, I would want to investigate more about the north and south ice caps, to see if they're all water, like Earth's water, or if they're a different frozen liquid. Hi, I'm Calder, and this is my rover. I put some rubber sticky stuff on the wheels so it could get more traction, so it wouldn't just skid along. And then I also, since the solar panel couldn't work, I made kind of like a frame thing and put the batteries in it, kind of like a bottle. And then the frame, actually, I cut pieces off the cardboard so it could go into the grooves of the bottom piece there. And the wires of the solar panel kind of go around and connect inside of there, but connect to nothing. And so here it is going up over my map book. Thanks for watching.
I'm Alexandra Fujioka, and I'm 12, and I live in Sitka, Alaska, small town in southeast Alaska. If this is Alaska, Sitka's around here. With a switch on a board with white. That if it was going to Mars would be attached to a main rover. These cables would be carefully covered and just like set up the spool out type of thing. And then this is the rover itself. I even cannibalized a part of another project and tried to wire it together to make it work. Guess what? I eventually discovered we live in a rainforest, and there wasn't enough power, or at least the meter claimed to put about 3 volts so far with the solar panels tested it hooked up to this rover, didn't work. So after testing everything, even the jumper cables, of course we didn't test the voltage meter, I don't think, but like. Anyway, after testing all that, we eventually decided just to swap it over to a battery-powered rover with a battery pack that you could try to charge up using renewables, I guess, if you had a renewable charger. And because we live in Sitka, we get most of our electricity from hydropower, so I guess this even is a renewable rover if you can get renewable batteries to go in there, or rechargeables to go in there. We try to investigate the sedimentary formations on like the areas where there may have been water at one point, investigate the sedimentary formation there, and then try to get some nice pictures. Because I know that my camera, if you put a good camera on a rover, something with good optics on it, it should be able to give you some really nice pictures. Just you'd have to keep it closed most of the time to keep dust from getting on it, but you could get some pretty nice pictures. Or you could ditto your photos and take a flat frame, a calibration frame that shows where all the little dust specks are that you can then subtract out, and then you get a dust-free photo. Maybe trying to do some if would it be possible to put a retroreflector key on Mars and then maybe have beam a laser signal to the sun? I know they did it with rovers on the moon, which Mars had too much atmosphere and that would scatter the laser.
Applause. That was wonderful. Thank you
Yeah.
to both students for putting together your rover designs. I believe there's a few comments. I see some are typed in the chat window, so don't miss them if you're in there. Ralph, do you have any comments on the two rovers that you saw?
Yeah, well, those were great presentations. I guess both struggled with just how much sunlight there was. It sounded like there wasn't enough current. I guess I'd ask though, maybe first to Calder. There wasn't enough current to drive the motor with sunlight, but you had the solar panel horizontal. And I wonder, because the sun wouldn't have been directly overhead, even in October in Alaska, whether you might have tried tilting it so that it was directly on to the sun. Is that something you tried?
Kind of, with the pen in the middle, so it could move. But
And the motor didn't turn at all. That's too bad. They should have given you bigger panels.
That's right. So more surface area would have been helpful, right? But if I'm understanding, Calder, you did try and angle it. That was a neat suggestion, Ralph, to have it, instead of having it flat, to have it angled, but the pen just didn't hold it in any one position. So, got it.
yeah, it just wasn't stable.
All right. Thanks, Calder.
Yeah, and I noticed Alexandra had some very interesting ideas about rovers on Mars, and I think you mentioned the idea of a laser retroreflector. This is just a kind of a prism that bounces a laser beam back, and the Russian Mars rovers had one, which we've been able to measure from the Earth over the years. I believe InSight, the lander that I'm working on, has such a retroreflector, and I think the Perseverance rover that is on its way to Mars right now has one. So there's a lot of other smart people with the same idea. And you also mentioned the idea of taking what's called a flat field, a sort of reference image, to calibrate out to compensate for specks of dust that might be on a camera lens. And indeed, that's something that astronomers do all the time, and people using rover camera images do. The InSight lander has a camera, and I'm afraid I've not got a before and after picture in the presentation, but when it landed, the rocket exhaust was blasting on the ground just a meter or so away from the camera, and it blasted some dirt onto the camera lens. And it looked pretty horrible, actually. But over the following, what was it, about 5 or 6 weeks, the wind direction changed, and then the wind was able to blow the dust away. But you're right, taking a reference image is a good way of fixing that. You mentioned, Alexandra, using a voltmeter. Did you, by any chance, measure the current put out by the panels? I'm just curious what that happened to be.
I think that's what we used the voltmeter for. And the power reading, I think the motor was a 6-volt motor, and the power readings, but it could operate on as low as 1.5 volts in theory. In practice, I think we got like 3 point something or so with the entire rigged up and cannibalized setup, and it still wouldn't even spin the motor at all. We were putting it like directly under a bright light and stuff, which wouldn't even have, I wouldn't have been able to get it that close to a bright light while trying to do actual test runs, but I just couldn't even spin the motor gears at all. So I eventually was like, let's swap the batteries. They are more reliable.
That sounds like you did the right thing.
Very cool. Well, thank you to both students. Alexandra, I wanted to mention also your comment on investigating sedimentary areas, and that is what the Curiosity rover did. Curiosity landed at the bottom of an alluvial fan. So it's an area where sediment has built up, and of course it's bigger at the bottom and then it's narrower at the top, so it has a kind of a fan shape, and it's investigating that sediment at that alluvial fan spot. So check out what the Curiosity drove all over. Unlike the lander that Ralph is going to tell you about, Curiosity was a rover that drove all over. I didn't mean to rhyme, but there you go. So that was part of its investigation. And yes, Ralph did, I'm looking at the chat, Ralph did mention that was a Russian moon rover. So we can provide, I'll look that up and send a link to that while Ralph is presenting, if that's okay. Right? Did I get that right, Ralph?
Sure, that's great. Thank you. Yeah, okay. Lunar cod.
Okay, thank you. I will look it up and put a link in there. Awesome. Yes, Mount Sharp is right where it landed. Yes. Good job. All right. Well, it sounds like you are really on it, and I am delighted to share with you Ralph and what he's going to present. Ralph has written books, as you'll see. He is immersed in this topic, and he is an expert. And I'm so glad that he can be here with you today to tell you about the work that he has been doing and is doing. He has a question in there for you to think about, so get ready. We're going to ask for your participation a little later. But at this time, I'll turn it over to you, Ralph, and I would love for you to share the presentation you have.
Okay, well, thank you. Let's see. Right. Sharing. Oh, did I? Oh, there we go. Let's see. So are you seeing it come up full screen?
We are, and it probably, it went away, but yeah. And it kind of looks to me like maybe a sunset you're seeing in Alaska. So we're going to talk about that and think about why that might be too.
Yeah. So as I talk about solar power on Mars, I'm Ralph Lorenz. I'm a planetary scientist at the Johns Hopkins Applied Physics Lab in Maryland. And the InSight project is one of several things I work on. This is, as Bonnie says, a Martian sunset observed by the Curiosity rover. And we actually use the word sol to refer to Martian days or Martian solar days specifically, just because the Martian day is close enough in length to the Earth's day, 24 hours, 37 minutes or whatever, that you'd get confused if you just use the word day. So if you use the word sol, then at least you know which kind of day you're talking about. So I'm very happy to be speaking with you today because I love talking about my work. I basically live the dream. I get to.
I've been watching. See.
I think. Is
I'm
there an
sorry,
open mic?
somebody's not muted. If you could just all please mute your mic so we're not getting any background noise. Thanks so much.
Yeah, so I live the dream. I was really interested in space as a kid, and I get to work on it every day. So I'm speaking to you from Maryland, where the sun set about about 3 hours ago, 2.5 hours, 3 hours ago. It's well and truly dark. Obviously, your longitude over in Alaska, the sun is still up. It's very low in the sky, I guess. I actually come from over here, Scotland, in the north of the UK, at about 50 degrees north latitude. So I'm familiar with long winter nights, not quite as cold as Alaska because we're kept warm by the Gulf Stream. Over the years, I've worked in a couple of places. One is the European Space Agency in the Netherlands up here, and for many years I was at the University of Arizona in Tucson. But it's just fun to sort of have this view of our planet, showing where you are and where I'm from. My favorite subject in high school was actually chemistry, I think. But I knew I wanted to work on space exploration, and it was almost by accident that I got into aerospace engineering, the sort of mechanics of building satellites and how they operate, rather than astronomy. And I was very fortunate to get a job working on this thing at the right here, the Huygens probe, that was launched in 1997 to Saturn's moon Titan. And actually, much of my career has been on Titan. And from the Netherlands, I went on to back to the UK to do a PhD building one of the instruments on Huygens, and that was just a magnificent opportunity to actually work on something with your hands that is now sitting on another planetary body. And I had to wait for 7 years for Cassini and Huygens to get to the Saturnian system, and the instrument that I built actually only worked for 1/20th of a second, but that was as long as it was supposed to work. So that was a real career triumph. I then, while Cassini was on its way to Titan, actually, I got involved in Mars in a project called the Mars Polar Lander that was to visit the South Pole polar regions of Mars, and that spacecraft was actually lost. There was a problem with its landing legs, and that's a feature of space exploration. It doesn't always work the way you hope, but you dust yourself off, you try again, and you have to be patient. Space exploration takes a long time. Since I've been at APL, I got involved in a Japanese project, the Venus Climate Orbiter, which is still in orbit around Venus right now, and is yielding some really interesting data. And I work on InSight, as I'll discuss. And my big thing is actually Dragonfly, sort of octocopter lander for Titan, because Titan has a thick atmosphere and low gravity. It's very easy to fly, and Dragonfly will let us explore, much like a rover, but we will be able to fly for several kilometers between each site we explore. And that's a really fun project to work on because there's lots of different aspects to the project that are about aircraft, are about drilling, that are just all the challenges of operating a vehicle remotely in a challenging environment. Anyway, enough about me. I do like to write. I think communication is a very important part of the scientific process. I mean, if you try hard, you can solve the equations, you can do the experiments in science, but often the hardest bit is persuading all the idiots out there that you're right and that you did the right experiment, and maybe their solution was less right. And I'm fortunate in that I've always enjoyed writing and communicating that way, and you can look me up online. Anyway, power. It's hard to do much in space without math. You need to ultimately think about the numbers, and whether something works or it doesn't often comes down to evaluating things quantitatively. And you're probably familiar with the powers associated with different systems. I mean, a 60-watt light bulb is a kind of familiar object. 2 kilowatt electric fire, and for perspective, 2 kilowatts is about 3 horsepower, and auto engines are several tens of horsepower typically. Whereas if you go to something small like a phone, it's maybe being charged with only 5 watts, and you need to think about just how much power is needed to turn a motor, and whether a given battery size or solar cell size gives you enough. For spacecraft, you have a similar sort of range. If you're doing energy-intensive things like cooking material to analyze them, or if you're using a radar where you're sending out energy and then measuring what comes back, that can need kilowatts of power sometimes. But simple passive measurements like weather stations or seismometers or cameras typically only need a few watts. But getting the data is only half the story. It's no good sitting on the measurement platform on the satellite or lander. It needs to come back to Earth, and that's a long, long distance. And so you need actually a lot of power, a lot of energy for every bit of information that comes back to Earth. So if you're sending lots of data, like radar images or whatever, then you need lots of power in your transmitter. If you're only trickling back a few weather readings, then maybe you can have a small measurement station with a small solar panel. But one thing maps to the other. The data requirements and the energy you need correspond. If you look at spacecraft designs, just by how they look, you can almost guess where they are in the solar system. All of these 3 satellites here, or satellites, have their main bodies. The sort of box is about the same size in each case, a couple of meters or so. But you can see those missions that are close to the sun only need small solar panels. Whereas if you go out to Jupiter, which is 5 times further from the sun than is the Earth, and therefore from what's called the inverse square law, means you get 25 times less power per unit area than we do on Earth. Then to get that few hundred watts to drive the spacecraft, you need huge solar arrays, and these things are the size of a bus, basically. And on the other hand, close to Venus, close to the sun, say at Venus, these short, stubby solar panels aren't even full of solar cells. I mean, there's lots of solar energy falling per unit area, and the challenge is the solar panels actually get too hot, and so you have to put half of the solar panel area is mirrors to reflect the sun away, whereas the backside can radiate the heat away. So there's, just from the sort of appearance of spacecraft, you can almost guess where they are. And then when you get to the outer solar system, like Pluto, for example, or even Saturn, for that matter, or Titan, there just isn't enough solar power to be practical. You'd need solar panels the size of football fields to operate a spacecraft system. And so there we often rely on radioisotope power, which is more compact and doesn't require large areas. Coming now to Mars, Mars is a planet like the Earth, and it has an obliquity like the Earth. The polar axis is tilted, and so Mars has seasons. These are, like Earth, not terribly important at low latitude. Near the equator, the length of the day is almost always the same. There is a bit of an effect on Mars, which is more significant than at the Earth, which is that Mars's orbit around the Sun is not circular, is appreciably eccentric, such that Mars is about 10 or 12% further away at aphelion, which happens to be northern winter, than at happens to be northern summer. Southern summer is shorter but hotter than northern summer. So you have these sort of unequal amounts of energy per day that you can get. And in southern summer, you get more potentially at the peak of summer solstice. On the other hand, in winter solstice, the sun never gets above the horizon, and that's obviously something that occurs in Alaska, or at least the north of Alaska. And so, if you're designing a Mars rover, and I guess one of you mentioned exploring the Martian polar caps, you would need to think carefully about which season you went and how to design the solar panels accordingly. And at very high latitude, the sun will never be overhead. It will, during summer, it stays above the horizon 24 hours a day, 24.7 hours per day. But it's never directly overhead, and so maybe you would have tilted solar panels, something to think about. Anyway, the rovers that have been to Mars, the first one went in 1997 with Mars Pathfinder, and it was the size of a small microwave oven, a laser printer perhaps. So it had only 1/10 of a square meter of solar panel. And if you sort of multiply the 1 kilowatt per square meter of sunlight on Earth, divide by 2 roughly for being less on Mars, take into account the fact that solar cells only convert about 10, 20, 25% of the sunlight into electricity, then that you can see that the sort of numbers, broadly speaking, add up. But you only have 20 watts to work with, which isn't an awful lot. And the way the rovers usually work is that they sit and charge up a battery with the solar panels. And the higher activity things like running the radio transmitter or driving only happen for a small fraction of the time. And the same is true for Dragonfly, incidentally. It's not peculiar to solar power. Now, something that was noticed on Sojourner, this first rover, was the power output from the panels declined during I forget how many it was like 80 sols, 80 days. The power fell by about 0.25% per sol, and that experience kind of conditioned expectations for the next set of rovers. And this degradation was due to dust drizzling out of the atmosphere during the mission. And so the expectation was that the Mars exploration rovers that went in 2003 would only last about 90 sols. Because if you multiply 90 by 0.25% per sol, then you would lose 25-30% of the capacity after that time. And you can't make the panels too big because then they don't fit inside the capsule, and they've got to unfurl and be strong enough not to vibrate too much when the thing drives. And so it was limited to about 140 watts peak power. Sorry, there were two of them, Spirit and Opportunity. I saw there were some questions in the chat, but what I'm going to do, I think, is go through the presentation and then come back to them, if that's all right. But there was actually something of a surprise for the Spirit and Opportunity rovers. Although the power output declined as expected, it's sort of leveled off a little bit. And then 400 sols in, which was already much more mission duration than they expected to have, there were these big jumps where basically the power output was restored. And what we think caused this was dust devils. These are whirlwinds that are caused by the sun heating the ground, and they can make tracks on the ground where they lift up the dust. And because these clearing events that made the panels work better again happened basically in the same season when dust devils were seen in the cameras, we think that it was dust devils that were responsible rather than just any old random wind gust. So that was exciting, and of course the Mars rovers actually ended up working for a couple of thousand sols. Now InSight is a lander; it's fixed. It's also at low latitude, so it works fine with the solar panels horizontal because the sun kind of goes overhead or within 20-some degrees of overhead every day. But you can see in the pictures that in the roughly 2 years since Mars landing, the panels and everything else have got rather dusty. And that was expected. But unfortunately, when you look at the current coming out of the panels, and this is just a part, I think the main panels put out about 6 amps each. The output declines, and some of this wiggle is due to the Martian seasons, right? It's due to Mars getting further from the sun. Part is due to the steady accumulation of dust on the panels, and unfortunately, you don't see any of those clearing events. The trend is almost uniformly downwards. There was a big drop in the first 50 sols, or just after the first 50 sols, and that was a major dust storm. That was dust in the atmosphere blocking the sun. Some of that dust then fell onto the panels. So it looks like InSight has been a little unlucky in that it has landed at a place that was good for doing seismology, which is its main investigation. But it seems to be in a place where the dust devils are not very strong. In fact, we haven't seen any in the cameras. Okay, here's the little puzzle for you. So this top plot is a plot of the solar ray current. It's actually generated all throughout the day. This is a continuous curve, but we only get the data when the lander is awake. Most of the time it goes to sleep. So you see sort of a rather smooth profile that comes up from 0 at dawn, or actually just before dawn. There's a little bit of twilight, and it declines to 0 near dusk or just after dusk, and it's at a peak around midday. But when you look really, really closely, there's a little dip on 1 or 2 days. In a couple of instances, it's been a couple of tens of %. But in this instance that's shown here, it's only a 1% dip, but it's very consistent. All these little data points are individually good measurements, and they show that there was maybe 0.8% drop, and this lasts 100 seconds. So, would anyone like to guess what happened?
And you're welcome to unmute your mics. I would ask students if you have a guess, or just take a guess and go first. What could cause that's a pretty sudden drop in power, correct, Ralph? It's not a gradual. Yeah. Yeah. Very short term, but sudden drop. So what could cause that?
Well, somebody just suggested in chat a loose wire. Well, that's an interesting thought. That would be a worrying thought. But you can see it's a rather symmetric profile. If it was a loose wire, you would get a drop you get a drop to 0 if it was the whole panel. But it would have a square bottom, right? The current would get cut off, and then it would probably get cut on again, right? A wire is either usually connected or not. It wouldn't have this sort of symmetric curve to it, I think.
So the
actually, I'm
chat's
gonna,
scrolling quickly. I don't know if you can see the other
yeah,
answers. One
I
was an
can't.
eclipse. Okay, and I'll read them to you. One was an eclipse, solar minimum, ET, or a flare. There were some other guesses.
Okay. Well, ET, can't say it's impossible. There is a famous astronomer called Carl Sagan who said extraordinary claims require extraordinary evidence. So I think we'd want to eliminate all other possibilities before assigning it to
Could
ET.
Alexandra, I see you're unmuted. Did you want to give an answer? Sorry to
Shadow of
interrupt you,
something,
Ralph.
someone said?
But yeah, I see shadow of something. Alexandra, I'm just asking because I see you're unmuted. So if you wanted to say an answer, you can go ahead and do
was
that.
Deimos one of Mars's two moons? That's the only explanation I can come up with.
Well, that's a very good guess. It might not even be a guess. You're exactly right. Mars has two moons, and this one happens to be the smaller moon, Deimos. This was a different eclipse observed by Curiosity's cameras. Phobos, the bigger moon, the closer moon, actually blocks out about 30% of the sun, and but the Phobos eclipses are shorter, so they aren't actually as pretty as this. But yeah, this is kind of fun because this presentation of data, this plot of light intensity versus time, is what a lot of astronomers use to detect exoplanets, planets around other stars. Except they need a big telescope to do this, whereas on Mars we can see the shadow of these two moons because they're a percent or a couple of tenths of percent. So yeah, good guess. If it was a cloud, it would probably not be symmetric. It would probably be a lot wouldn't have as sharp a beginning, wouldn't have as sharp an edge. But yeah, it's a fun puzzle. So good guess. Thank you. So coming back to what InSight is doing, we, as I say, have not seen any miraculous recoveries of the solar panel output, and it might be that the progressive accumulation of dust on the panels is what will cause an ultimate end to the mission. Probably, a year or two away, I hope. We haven't seen dust devils in the camera pictures. You can see that this camera picture is maybe a little bit dusty. There's still a couple of dust flecks from when the vehicle landed. We have seen, however, a couple of little one sample dips, just little blips in the solar array current. And those might be the shadows of dust devils. I mean, they're only a 1% kind of drop, so they're not very dusty. So, we'll cross our fingers. Maybe we'll get lucky and a dust devil that's strong enough will come along and clean the panels. We know there are lots of whirlwinds because we can see the pressure drops that happen, and that we see the stronger winds that are associated with them, but no cleaning events yet. So stay tuned. And that's all I had. This is just some of the projects that are underway at APL where I work. But I guess I'm happy to take questions. I don't know if you want me to read the chat, or do you want to pick questions out of the chat, or how do you want to proceed?
I can read some of the ones that were in the chat. Alexandra had asked, which is a better deal for power on a Mars or closer to the sun, solar or nuclear? And I would like to talk about that because Curiosity and Perseverance are both nuclear powered. So that'd be a good point to cover.
Yeah. So the part of NASA that deals with these power sources, so-called radioisotope generators, works with the Department of Energy. And it's a very specialized, very expensive business. There aren't many applications of plutonium. So these power sources are are really reserved for those instances where they're essential. And New Horizons, that was built here at APL, that went out to Pluto, is a good example. So was Cassini at Saturn, and Dragonfly will be. Now, Mars is a sort of interesting case because clearly you can do missions that are solar powered, at least at the equator. You can do missions like Phoenix. So Phoenix was a mission that was basically a reflight of the Mars Polar Lander. It went to, I forget, about 60 something north during summer, and it lasted 150 sols here until basically the sun got too low. So if you wanted to study polar winter, where it's dark, you would either need a very, very, very big battery, or you would need a radioisotope power source. At low latitude, there's some sunshine every day, except when there's a dust storm. So it would depend on whether you needed to be guaranteed power. Mars is also very cold. At night, the external surfaces of landers get down to minus 100 Celsius, for example. And so that might be something to think about if there are very sensitive components that can't be so cold. Either you have to burn battery energy to keep them warm, or you need some other source of heat, like a radioisotope source. Going in towards the sun to Venus, the case for radioisotope power is not very strong. So Mars, there's a couple of specialized instances, but further out from the sun to Jupiter, Saturn, it becomes more and more important to have to supplement solar power.
Mm-hmm. So kind of along that same line, one of the questions was, would it be possible to have some kind of a brushing system? I'm thinking I could send my iRobot up there, right?
Yeah, that's a great thought, and there are a lot of discussions on the InSight project right now whether, if we don't have a brush. There's a sort of grapple which was used to put the seismometer out onto the ground. But could we sort of tap the solar arrays, or maybe if we hold the arm close to the solar panel, maybe the airflow might abrade the dust away better. A brush is certainly an idea for future missions. There have also been ideas talked about of using sort of vibration, putting a sort of little kind of rattler. That obviously works a lot better if the solar panel is tilted, so that the rattling kind of loosens the stuff and it will slough off. Another possibility is maybe some sort of electrostatic system that the dust kind of clings because it's charged, perhaps, and there might be ways of changing the electrical charge on the surface to sort of move the dust around. These have been thought about and prototyped, but not yet developed to a point where anyone is very confident in their application. This is definitely an area that could use some good ideas and future research.
There we are. So that's an assignment for you students. Get thinking on that. There's still a lot for us to learn. And that's true about the solar system in general. There's still a lot to learn. For as much as we have learned, there's still a lot more to learn. So lots of space for you to come and work with us. So I read through, and I think I got the questions. If I missed a question in the chat that you wanted to ask, please go ahead and unmute and ask your question. I did find a lot of great answers when I was scrolling through there also. So it was good to see those answers that I had missed previously, and I was sending some congratulations out for that. Christy, do you want to ask your question?
Sure. My bachelor's was in soil science, so anytime somebody says that dust has a charge on it, I get really excited. So is the dust positively charged, or those cations? And then how does that affect, any kind of current, or, I'm wondering about the charges on Mars compared to the charges on Earth with dust.
Right. Well, the many of the minerals are going to be the same. Mars is covered in a lot of volcanically derived basalt dust. I can't remember off the top of my head which is the preferred charge direction. I know I've done experiments myself with some sort of soil mechanics and found that you can get charging of either sign. And in fact, when we study charge in dust devils, the charge is size dependent, right? The coarse sand gets charged in one sense, and the finer dust gets charged in the other sense. And the result is that there's an electric field associated with dust devils when they go past. It's actually a very good way of detecting them. But I can't recall offhand which ions might favor one charge direction or the other. It'd be a good project.
And Brooke is guessing. Brooke, did you want to ask your question? And Calder, you can be up next after that. Brooke,
Oh,
did you
no,
want to ask your question?
I was just, when you guys were talking about the charge in the soil, I was just wondering if it had to do with the elements it was made out of. Not really a question. I was just kind of trying to be
No,
part
that's
of the
okay.
conversation.
That was good. And you were mentioning that it's high in iron, right? And that's why we think of Mars as the rusty planet, the red. But is it in fact iron, Ralph? I'm checking myself there.
Yeah, that's exactly right. The minerals like hematite was famously discovered by one of the Mars rovers. Maghemite. We know there have been experiments on Pathfinder and other missions where they put little magnets where the dust can where we should expose the atmospheric dust, and they clearly stick. The dust sticks to the magnet, so it's magnetic. But yeah, your intuition that rusty red means iron is dead right. There looks like there's a question from Calder suggesting could you have wind power? That's a really interesting idea. I have seen some suggestions of wind power on Mars. What you need to think about is that while there can be quite strong winds at Mars in terms of wind speed, the Mars atmosphere is about 50 times less dense than Earth's atmosphere. So for a given wind speed, there's 50 times less power. And this is why it's difficult to fly on Mars. You may know that the Perseverance rover going there now has a little, 1.8 meter diameter helicopter that's going to try it, and it's really hard to get that thing to work. It's really cutting edge aerodynamics. Titan is way easy, so we'll see how well that works. But solar arrays have the advantage of no moving parts. You just, as long as they see the sun, they generate power. There's no danger of dust getting in the bearings that might cause the bearings to seize. So it's not impossible to imagine wind power on Mars, and it might be a good supplement. But can you rely on it? Are there going to be calm periods when there's no power available? At least with sun, you can mostly predict when those happen. It's nighttime or is dust storm season. But good idea. But there's some caveats. Looked like there was a question scrolling back here from Alexandra about the APXS. So this was an instrument that was on the Sojourner rover. I think I can. I stopped sharing, I think, didn't I? Let me see if I can share again. Share screen. Did that happen? Yes, there we go. So what you hopefully can see is that the Sojourner rover is sort of sniffing a rock. It's quite deliberately parked with its front end up against this rock. And the little sort of cylinder you can see there is an instrument that has a little radioactive source that puts out alpha particles, and it measures the radiation that's bounced back. And that radiation is diagnostic of the elements, specifically the elemental composition, how much iron, how much aluminum is in the rock. And this APXS instrument told us about the composition of several rocks at the Pathfinder landing site. So I think it's not a very power-hungry instrument because it's passive. So it's shooting out particles. Those particles are the product of natural radioactivity, and so the instrument just has to sort of, listen for the particles coming back. So it wasn't a very power-hungry instrument. It was able to run on the 16-watt average power of the rover. Let's see, stop sharing so I can see the chat again.
Yeah, I found one that I missed as well. Did they manage to fix the tunneling probe on InSight?
Oh, yeah. Yes. InSight has an instrument called the Heat Flow and Physical Properties Package Probe, I forget, which is basically a sort of self-hammering drill or mole that is supposed to sort of pound itself into the ground, actually down to a depth of 3 to 5 meters. And it drags a tether behind it, and the tether has little temperature sensors so you can measure the thermal gradient. And the thermal gradient tells us how much heat is coming out of the Martian core, and so tells us about how Mars has evolved as a planet. Unfortunately, the probe was emplaced correctly and started hammering down fine, but then kind of got stuck. And we don't know if it was sort of perched on a rock or if there was something unexpected about the soil mechanics, the regolith. In particular, to sort of hammer itself forward in one direction, it relies on friction along the walls of the cylinder. And it seems that the ground was had enough porosity, had enough empty space in it, that the mole sort of made a little cavity for itself, and so it just kind of pounded in place without getting any grip. And this wasn't something that had been planned for. And we've tried a number of things like sort of pushing it down with the scoop, and that helped a bit, but then it sort of bounced back out. So we pushed it back in again, which is a very slow process because you have to develop all the commands for the robot arm to precisely push it in without being in any danger of cutting the tether. So you have to spend basically days or even weeks between each sort of exercise, and then you see how well it's worked. So the last few weeks, months even, we've been sort of scooping now dirt and sort of piling it into the hole behind the mole with the hope that it will have enough friction to finally get going. So that, I think, is maybe not going to happen quite till the start of the new year. I think there's a plan to maybe do another scoop. So we haven't given up on it yet, but it's probably only got 1 or 2 final shots to get going. It is at least beneath the surface now, so it will yield some information on the thermal properties of the near surface material, but it does need to get to 3 meters to get the heat flow measurement it's really intended to do.
Mm-hmm. All right. Well, there are a couple more questions, but I want to be respectful of your time, Ralph, and everyone else's time also, because we're a little bit over an hour now. We didn't start right at 7:30 or 3:30 your time, so we're a little bit over. So I guess one thing I'll first ask is, Ralph, would you like to take 1 or 2 more, or do you want to cut it off here?
I'm happy to take questions for another 10, 15 minutes if you like. I mean, like I say, I live this stuff, right? This is
right.
This is the most exciting thing I can imagine doing with my life, and and now I get to talk about it with interested people.
Right.
So
Yes.
I stop.
Okay, well, I'm very delighted to hear that because I do think these are great comments and questions. So then I'll just say to others, if you're feeling like you need to go, you are welcome to go ahead. We won't be offended, but I agree. This is really interesting, and I'm so delighted to have the connection of you here interested to ask Ralph questions. I'm happy to keep going myself as well. So let's not go in order though. Calder's mom, I'm going to save your question and we'll kind of end with that if that's okay, because that's kind of a dreaming question. And yes, if you want to say goodbye in the chat, I completely understand. But let's see, let's start with, I saw you had one, Christy, but I'm going to go first to Alexandra. Alexandra is asking, how do you know so much about Mars? And I think that's an interesting question because I understand that you went to school and learned this, but where did the curiosity come from? You know, talk a little bit about how you got into learning so much about Mars and astrophysics in general. Oh, and Ralph is looking, there you go. I was going to say Ralph looked frozen there, sorry.
No, I'm just puzzled because the question was from Christy to Alexandra, why she knows so much about Mars.
Oh, I misunderstood. It is.
I have to say I'm curious
so,
myself.
So there we go. Then let's defer. Thank you, Ralph. I did not catch that. I was just reading the question. Go ahead, Alexandra.
So I've been into space for years since I was really little. I've been like, ooh, this is really cool. So guess what? I kind of got more and more interested, and now I'm doing basic astrophotography.
Sweet.
Yeah. Getting my first DSLR ordered, hopefully this long weekend coming up, if everything goes right.
Cool. Well, I wish you clear skies. I used to do some amateur astronomy when I was in Tucson, Arizona. It's very dry, and so the sky is usually nice and clear, and they're actually quite careful about making the street lights not have too much light pollution. But here on the East Coast, it's cloudy, it's humid, it's buggy. There's lots of light pollution. It's a lot less inspiring for astronomy. Let's see. Looks like there was a suggestion from Tyler. Could you install magnetic strips in between the panels to coax the dust away from the cells? That's a really interesting idea. I know there was actually a recent paper looking at the magnetic target on Curiosity, the Mars rover that's there now, and indeed the patch of, I guess it's plastic, maybe it's aluminum, the patch of the housing that's next to the magnets is less dusty than some random part of the rover surface away from the magnets. So it might buy you a little time. But magnets are often quite heavy. So you would sort of need to think, if I have 1 kilogram extra to spare, and the size of a launch vehicle, the rocket, is often limited in how much mass it can throw to the planet. If you had 1 kilogram to spare, would you spend it on magnets, or would you just have a bigger solar panel? That's the sort of what we call a trade-off that engineers have to do all the time. What is the optimal, most efficient way to solve the problem? Let's see. Would it work to use solar energy to heat a fluid and use that fluid to power the rover? That comes down in part to efficiency and in part to the mechanics of doing things. There are, for example, in, I guess it's Nevada, I sometimes see it from the plane back when I used to be flying around all the time. Flying to California, you can see this huge solar power plant in Nevada. And there's like football field-sized arrays of mirrors that point the sun to the top of a tower, or 3 towers. And I guess there's actually salt there, and the solar energy gets so concentrated that it melts the salt, and the salt stores the heat, and you run a turbine with steam like you do in a regular power plant. And that's efficient to scale up, when you're talking about hundreds of megawatts. because to make it more powerful, you just add more mirrors. But the smaller you make something, to say have a kilowatt for a rover, the less efficient things tend to be because they're smaller, heat can leak away. You also have reliability considerations. Turbines are moving parts, and so could they seize. Whereas a solar panel just sits there. Okay, if you want twice as much power, you need twice as much panel, but you sort of know what you're going to get, and it's always going to work, and there are no moving parts. So as long as we're talking about robots kind of running around making scientific measurements, probably solar panels are the way to go. If we get to, some decades, centuries from now, where we have, bases on Mars with human beings, they're going to need, tens, hundreds of kilowatts of power. And what's the right answer there? Is it solar panels? Is it solar energy heating a fluid like these solar dynamic, or is it nuclear? I don't know. Is it wind? Maybe a mix of them. That's a really interesting problem to think about. But for rovers today, solar panels make a good option, or these RTGs that Curiosity and Perseverance use. Let's see. Have we got all the questions? Have I missed any? Oh, Calder's mom. Oh, endless money and staff. What would I do with a rover? Well, send it to Titan for a start. Titan has a landscape much like the Earth. It has rain, has rivers and seas, but under very exotic conditions. Right, it's very cold because it's so far from the sun. So I would like to explore Titan with a quadcopter, which we're going to do with Dragonfly, but that's going to only explore a few hundred kilometers, and Titan is a big world. I think it'd be really interesting to explore Titan's seas. It has seas near the North Pole that are full of liquid methane on Titan. Because Titan is so cold, methane, which we know as natural gas on Earth, is actually a liquid. It behaves in much the same way that water does on Earth, evaporating, forming clouds and raining down. So exploring Titan would be more of what I would do. All right.
And there was one there from Christy about the fact that there's a different kind of weathering. There's not water running on the surface of Mars. So how does that affect the particles and their shape, as opposed to on Earth, how things are weathered by water?
Well, so that's a great question. Very interesting. And actually, let me jump to the moon for a second. Basically, the terrestrial planets, so not Titan. Titan is organics and ice at the surface. But the moon, Earth, and Mars are mostly made of silicate rocks, like basalt, which is a common volcanic rock. And the moon dust is basically pulverized basalt. There are micrometeorites that hit the lunar surface, and they make little craters. They break up the rock, and these fragments are really angular, and so moon dust is really, really abrasive because it's got very sharp edges. And in fact, the seals on the astronauts' gloves during Apollo were very close to actually getting abraded to the point that where they'd fail. Moon dust is really nasty stuff. On Mars, it's true that there isn't liquid water, at least most of the time. There might be one or two specific sites where perhaps some springs drain out before the water freezes and then sublimes. But generally today, Mars is dry, and you're quite right. But Mars was probably wetter, at least for some parts of the past, at least in some places. And so the processes that make clays, for example, which are associated with water on Earth, have happened in the past. So weathering today is probably not exactly the same, but there may be an inventory of water-mediated dust particles, let's call them. How much they contribute versus sand grains abrading as they blow around. But again, because there's wind on Mars that's moving the sand grains at least get a bit kind of abraded and polished. They're not as angular and nasty as the moon stuff. But it's a great question. You need a sort of microscopic imager to look at the grains at the micron kind of scale to have a perspective on these.
That was great information, yeah, and definitely something to keep in mind as we're thinking about going back to the moon, because spacesuit design is a very critical part of the success of that mission because of the problems. The particles, Ralph mentioned that the glove closures were abraded, and the other problem was the particles got deep into the layers of the astronauts' spacesuits, and that was a problem. And so we need to worry about that or deal with that, I guess is a better word, as we think about going back to the moon. And Ralph, I'm glad you said about the water, because we do see evidence on Mars, that is, because we do see evidence of some rills, a feature that we know to be caused by water flowing on Earth. And there's been pictures where, you look at it in one season, you look at it in the next season, and the rills are different. So it's interesting as you look at that. And Alexandra, as you're doing photography and looking at photography, looking for features on other planets, when you know how those features are caused on Earth, can be a really good research and way to find out about that planet. So I'm glad you brought up that possibility of flowing water from time to time, Ralph. So, all right, well, I think we'll end there. We did post some other, NASA has a variety of different citizen science projects where you can investigate some pictures that have come back from rovers and other probes and landers. And so Christy posted some. I know I posted some more. So if that kind of research is interesting, there's plenty of work to be done as a citizen science, and certainly getting into school and becoming a scientist, as Ralph is, working on these projects is a possibility as well. So thanks everyone for being here. Thank you very much, Ralph, immensely for what you presented, and also for sticking around with us to answer all of the questions. This has been a wonderful time together, and I say goodbye and thank you. And if you have any additional things that come up afterwards, send questions to DeShanna and she can get them out to us. Thank you everyone for being here today.
Thanks, everybody.
Thank you.
Thanks, y'all.
And thank you, Bonnie and DeShanna.
Thank you.
Anna.
And thanks to Shane as well.
Too. She's still on. Thanks, everybody. Yes, Anne, you're there.
Yeah.
This was so much fun. I learned so much from you, Ralph. I really appreciate it. I'm super motivated now. Like dirt! Yay!
Oh, dirt is really exciting. I agree.
And then when you were talking about, we need to do this and we have to shovel some more. And I'm thinking, gosh, it's like when I was a kid playing, but now you get to play on Mars with remote control. How cool is that?
But the frustrating thing is that it's taken almost a year and a half to try and get to the point where we think we might have the problem sorted out. But an astronaut there would, 5 seconds with their boot would have sorted this. But there you go. Okay, I'm going to sign off. It was really, really fun, really stimulating. Thanks for your interest, and
thank
I
you.
thought the students had great questions.
Yeah, thank you. And Alexandra and the students, they're future scientists. I love it.
Absolutely.
All right.
Yes.
Have a good holiday break. Thanks.
Thank
Yes, thank you. And thank you, Shane, for all of your efforts. Shane's behind the scenes over there. Thank you, Shane, for all of your help also.
Thanks, Bonnie.
Yes, thanks everyone. Bye-bye.